Well, thanks for putting with us. I know it's been a long ride to try to get these Kaggle project presentations done with. We're the Centaurs, and we're going to talk about our approach and our findings with regards to this particular project. I won't necessarily spend a lot of time going through the background and context of the project, since everyone here has worked on it and has already presented it and has listened to everyone else present it. So suffice to say that, same as you guys, we're using the Kaggle dataset obviously to try to build a classifier and derive insights from data that lists events and collisions, to be able to build a classifier that can identify whether or not an event was a Higgs boson to tau decay, or whether or not it was background noise, meaning another set of particles, processes, etc. that are not what we're interested in. So with that said, we are going to talk about the exploratory data analysis that we went through. So we'll talk about some missingness, some PCA, some correlation analysis, and so on and so forth. And then we'll talk about our ensembling, right? How we built our predictive model. We looked at 3 different models that we ensembled together. We'll go through that, and then we'll end up with room for improvement always, if we're so inclined. All right. So first of all, looking at the data set, I'm not sure why it's cut off at the top, but we started looking at missingness, right? Missingness in the data. So out of the 30 features, 11 had, roughly I think 11 had missing data. We looked at it in a bit more detail, and here what we're showing is that the missingness, for the most part, for 10 of the 11 features where there's missingness, it's related to the number of jets, 0, 1, 2, and 3. Jets being like pseudoparticles that are also detected, and a lot of these features that contain missingness, they're actually the missingness is inherently missing. I mean, it's not a fault in the detection or simulation process. It's the fact that if there are no jets, then those features don't make sense to have any values, right? So that's why for number of jets equals to 0, you have these features with missingness. If there's 1 jet, then the features that were related to having 1 jet, now they have some data. So you see a drop. And for events with 2 or 3 or more jets, all the features that were related to 1 jet, that were related to 2 jets, now it makes sense for them to have values. And the final feature that you see even here with missing data, that's the mass. So that's another feature where missingness isn't related to the number of jets per se. So the pi-jet number feature can be treated as a factor for missingness. And as we go through the models, we'll talk about how we dealt with that, depending on the model. Anything you guys want to add to that?
Nope.
Nope.
So that's why we didn't need to do any more feature engineering with the missingness, because this jet number kind of takes care of that.
All right. So talk about PCA.
Okay, so we've already seen people do PCA, so I won't go into similar results, but I'll just go into kind of a summary slide of what I got out of the PCA. So if we look at, as other people have shown, I chose about 9 principal components. One thing that I noticed out of this graph when you plot PCA, the first principal component versus the second principal component, is that you see some groupage. You see some clustering right here, you see another cluster right here, you see another clustering right here, where the other variables are less related to each other. So the big takeaway I got out of this was that one thing really stood out to me is that when I did, so I had all 30 variables, but when I looked at the derived mass and the label, they almost match up almost perfectly throughout all 9 principal components. So this shows to me then that the mass is very important as a predictor for the label or background or signal. So why is this? Actually, if you look at the physics of the Higgs boson, This first graph is from the science paper that they published on this. And they see that the derived mass is what they use to identify what's background and what's signal. So I've actually made very similar graphs in my PhD, but instead of giga electron volts, it's been hundreds of electron volts, so not as powerful. Higgs boson has a mass around 125, 126. And so this is the signal peak for the Higgs boson. While the background particles you see have other masses, the other biggest thing was the Z boson, which had a mass around 96. And that was our biggest contributor to the background noise. And when we actually look at, this is straight from the data that we obtained, you see a very similar graph, right? You have your signal, your Higgs boson, right at 126, and you have your background right around 96. Now you may notice actually that the proportions are a little different here, and that's because in the simulated data they weighted this data so that the signal was stronger than in reality. But I thought this was very cool actually, in that we first saw this in the PCA, and then we can actually use the science behind it to actually understand why this is true. Oh, yeah. Okay. Okay. Well, the correlation plot matrix, we've seen this a lot, and actually, I even got rid of the labels because no one's going to read 30 labels. And the point is that there are several regions of correlated variables. And so it's a very strong covariance. And well, I think everyone else in the previous presentations have hit the subject matter pretty well. Okay.
Thank you. So looking at the distribution of all the variables, we noticed that there were 14 features that had positive skew towards smaller values. So you can see there's a high peak here, and it's like clustered around here, and that was true for 14 of these features. So we went ahead and did a log transformation. And this is one example of the before and after the log transformation. So applying a logistic regression, I compared a saturated model, which included all the variables, and a stepwise BIC model. The reason being choosing BIC is because it has a higher penalty term than an AIC. Because of my objective was for description of our data set, that was the motive behind that. So in comparing the two models, you'll notice that we were able to eliminate a lot of the primary variables. So we ended up having more derived variables to go off of. Okay.
I'll just speak to this briefly. So since our approach was to try a bunch of different models, different algorithms, different parameters and tuning, we needed to make sure that we had a decent way to compare the performance of our different models. So we started with AMS because that's how the competition indicated in the documentation that they would be evaluating the different models. But we did some more research around it, and it seems like the AMS isn't very stable. And when we tried running a couple of simulations, using different seeds, taking different samples, it didn't seem like it was indeed very stable. So we opted instead to use the AUC. I mean, we also looked at the AMS, but we primarily looked at the AUC to compare different models. So this is basically is a ROC graph showing the AUC, and we'll have. I mean, we don't have these slides for every single one of the different models. But here we're just saying that, for the rest of the analysis that we've done, we actually use the AUC as a primary measure to compare the predictive accuracy of our different models.
Yeah, so understand that the AUC was our metric. I looked at how it applied to the logistic regression, and it improved only very slightly, but any slight improvement is pretty good. So yeah. Yeah, and comparing the deviance between the full saturated logistic regression with the BIC was slightly better.
For which model?
Sorry?
For which model?
So this is the saturated logistic, and this is the stepwise. Yeah, so it had a small improvement from 0.65 to 0.66 for the AUC. Okay.
Oh yeah. Okay, so we mainly use the logistic regression as to give us some insight on our models, on our data. But we ended up using 3 other models for the actual predictions. So our 3 models were Random Forest, GBM, and XGBoost. For Random Forest, the only tuning parameter that I looked at was the number of variables in a given tree, or randomly selected variables in a given tree. So at the very first, I wanted to get a pretty wide range to tune the variables, so I only used 20% of the data. I looked at it's misspelling, but looked at a grid of 1 to 9 randomly selected variables. And in this case, it chose 6 as the best model. And then with that as a center point, I then looked a little bit further. And 6 actually a pretty good choice because it's recommended for Random Forest to choose about square root of the number of features you have. And since we had 30 features, that falls right between 5 and 6. So then with 80% of the data, I fit the model, and it turned out that M-try of 5 was the best. So the AUC on the training data was 9.071, Kaggle rank of 1311, and AMS of 2.58. And I want to point out that I actually didn't fit 100% of the data to tune the model, but it had a perfect AUC, which I know in Random Forest you can't overfit. It didn't feel right. And actually, some people have gone both ways in the Random Forest during the presentations, and I would love to hear about anyone's opinions about why that is and why it still kind of works out. But for me, it just didn't. I felt uncomfortable fitting 100% of the data and getting a perfect AUC and trying to report that. So one thing we did discover with the Random Forest is that the variables that are most important, and going back to once again what I said earlier in the presentation, are related to mass. So the mass variables are the most important. And overall, the derived variables are also the next important, and then the primary variables tend to be less important.
All right, so the second model that we looked at was gradient boosting model, boosted trees. The tuning parameters, if you recall from class, the shrinkage, so their learning rate, how slowly or how quickly we want to learn, in this case, relatively slowly. The interaction depth, essentially the complexity of the different trees that we're building sequentially. The number of trees, how many trees we build sequentially, remembering learnings from the previous trees. And then finally, the minimum observations in a node, so not going down to the final observation within a node, but limiting it to prevent overfitting and for, I guess, computational efficiencies as well. So we ran through cross-validation and used a grid, and the values that we stuck with for after a 5-fold are 0.1. Well, you can see here 0.1, 3, 150, and 10 respectively, and that led to Kaggle rank of 1394, slightly worse than random forest. Yeah, I'll skip this, but.
Okay, and then we ran an XGBoost. So I'll go super quick. Since I guess we didn't learn about XGBoost, I had a very quick overview of what it was. So it's a gradient boosting algorithm that's fairly recent that allows for some parallel computing, more tuning parameters than GBM. And whereas GBM is completely greedy at every split, the way XGBoost works is that it actually allows for losses in the short term to possibly get greater gains in the long term. And so it runs this model and then kind of prunes the tree backwards to eliminate the losses at the end of the tree. And so it's generally faster and performs better than GBM. So XGBoost, I'll go through really quick. These are the parameters: number of trees, depth of the tree, the amount of parameters you sample at each split, the learning rate, perform cross-validation, got some tuning parameters, and got an AUC of 0.925, a Kaggle rank about in between GBM and random forest, AMS of about 2.5. The XGBoost very importance are very similar to the random forest variable, the most important variables. Like Yannick was saying, that the mass kind of shows up at the top and the derived variables. And then we ensembled these three models by a majority vote. So if you recall, the best Kaggle rank of the three models was the random forest at 1311. And so we ensembled them and we got to 1309. And an AMS slightly better than all of them. So what could we do better? We pretty much didn't do any feature engineering. So there was some basic physics things, which some of the groups have talked about. There are all these angles that are correlated, and you can do some rotations with these to make them more meaningful. The Cartesian coordinates of the momentum apparently work better. There are some more advanced variables in the forums. This cake variable came up a lot. Cake was a Kaggle team, and that a lot of the winning submissions included this variable. And we'd like to, before actually including these in our models, we'd like to actually understand what they mean, which we weren't completely able to do. Incorporate the log transforms that Wanda was talking about. So generally, when you have a variable that's highly left skewed, taking the log transform of it could help in the modeling, and so doing that would be great. And as far as models, incorporating more models, a neural network, what have you. Some more sophisticated ensemble. So our ensemble didn't do too much better. So doing some stacking, running different random seeds for the same model, ensembling these. So these are some things that we could do to improve. So that's it. Thank you.
Sure.
So you mentioned choosing
Yeah.
the VIC for descriptive purposes.
Oh, sorry?
You mentioned using the VIC for descriptive purposes.
Yeah.
So we have a more parsimonious model here.
Yeah.
What is one more improvement that could add to your piece here that goes along the lines of using the VIC for logistic regression?
Another piece of improvement?
One of the biggest benefits of things like simple, multiple, linear, and generalized linear models is that we get coefficients.
Yeah.
And since we're using the VIC here, we have the importance.
Mm-hmm.
But maybe it would be nice to interpret one or two of those coefficients.
Yeah, absolutely.
That's something that I don't think anyone did in the other projects, but that would add a lot more insight here.
So looking at the betas.
Yeah.
Okay.
The betas, even if it's just one or two of them, the highlights, just like I guess Yannick did.
Oh, okay.
For all the principles on, but gave a highlight there. That would add a lot more flavor to this.
Like the change between the beta from one to the other, or
No.
No.
Just like the beta coefficient for one
Yeah.
of the prime variables was 0.5. What
Okay.
does that mean in terms of logistic regression? Oh, reduces the log, whatever it is, whatever.
okay, sure.
Someone, we kind of talked about this on Tuesday, but can someone please interpret sensitivity against specificity for an AUC?
Sure.
Everyone just keeps putting these up there, and no one's interpreting it. I think it's very important that we have a clear understanding of what this is telling.
And I wasn't here on Tuesday, so this is going to be fun. All right, so what this shows is for, well, sensitivity, you can consider it the true positive rate, meaning a classifier, if it classifies something as positive, is it truly positive? And specificity, you notice that it's actually lower on the right, higher on the left. That's the true negative rate. In some other graphs, you might actually see it directed the opposite way. That would be considered like 1 minus specificity. That would be like the false positive rate, if you will. I mean, they're related, just depends on how you want to view it. So the different curves, these are basically for every threshold, like what's the balance between sensitivity and specificity for a specific classifier. So case in point, if you're all the way up here, for example, I mean, if a curve's like going out that way, the closer you are to this corner, the better your discrimination of your classifier, right? Because you basically have a really high true positive rate and a really, I guess, high specificity or low false positive rate. So if your curve, like the higher and closer it gets to the top left, the better. If it's at the diagonal, it's basically a really poor classifier because basically you have the same chances of being a false positive or a true positive at that rate, right? So that's kind of the ROC curve. Now, the AUC, the area under the curve, if I remember correctly from my research, it's basically the probability that if you were to take like one observation from one group and one observation for another, the classifier would classify them appropriately, right? If you take in this case, you take a signal, you take a signal from the population, you take a background event from the population, what's the probability that the classifier is going to classify them properly? Signal being signal, background being background. So if we were to overlay a whole bunch of these here, you might see another one like that. That wouldn't be a very good model. You see this one, it's a better model. You see that one, that's an even better model. Yeah, that's my interpretation of it.
And someone else give me the answer to how the curve is actually generated.
Sure. So a bunch of different thresholds are tried. And so say from 0 to 1, right? So we're used to, say, 0.5, less than 0.5, we say, that it doesn't happen. Greater than 0.5, it does happen. And then you say how many true positives do you have? How many false positives do you have? So with that 0.5, you do the same procedure for a wide range of things between 0 and 1. So for all these values, we do that, and those are actually, there are kind of lots of points on this curve. And this like 0.381 is the optimal threshold where you get the greatest, what's the word I'm looking for? Discrimination between the two groups. Is that what you're looking for? Right.
Particularly because it takes the prevalence into account. But having a higher AUC is not always better than another model that has a lower AUC because it depends on the kind of variable. And that's one thing that we're kind of glossing over here. I
actually answer my question about the random forest? So when I did 100% of the data, I got a perfect, it just went right to the left corner, top left corner.
Yeah, so that means that you have no false positives
Right.
or false negatives.
And I was like, that seems like overfitting, but it's random forest, so you can't overfit.
Yeah, so random forest can overfit in one sense, but in another it can. So on your training data, you were able to get perfect classification.
Yeah.
But we're not overfitting to, if you try it on a test data, you probably have some errors.
Yeah.
So we can talk about this in a little more detail, but random forest cannot overfit in the sense of modeling the noise in your data set by building too many trees. You can overfit a single, let me clarify. You can overfit a single decision tree, right, by just building it out too far.
Yeah.
But you can't overfit random forest. Let's assume that we have no overfit individual trees by adding new trees. That's what we mean by you can't overfit random forest.
Yeah.
You could potentially have an ensemble of trees that overfits, which would mean that random forest overfits, but that would be the assumption that the individual trees were built in a fault. So yes and no, you can overfit a random forest, but that's under the assumption that you built the tree. Does that make sense? Am I confusing anyone there? The clarification about not overfitting with random forest is by adding additional trees.
Mhm.
You can't. You can overfit in other ways, but by adding additional trees, you can. Does that make sense? All right.
Okay, how did you guys handle distribution of data? I think I missed that part.
Yeah, so for all the tree-based methods, kind of handle the missingness automatically. So the answer is that we didn't do anything.
Also, you talked about parallel processing.
Yeah.
The XGBoost. Can you just talk a little bit about how that?
So I actually don't know how it works, right? Because it can't be truly parallel because it's a boosting method, right? So the results of the previous step do depend on the results. The next step depend on the results of the previous step. So it can't be like truly parallel. So I don't know I mean, I don't know the technical details of it, but I know that kind of wherever possible, they've optimized to do as much parallel as possible. It's not like actually parallel.
So that means they just say, do they put some using the multi-core in your computer?
So they definitely do that. And again, I don't know exactly what it is, right? It can't be that you're building different trees with each core because one tree depends on the previous tree. But there's something that it does that does optimize it better than GBM, for example.
Parallel computation normally doesn't mean 100% zero, but you actually one matrix you calculate different core and look together. But this costs more time. Parallel definitely not mean 100% zero. This one tree, that tree can handle the same tree together.
Right,
Yeah.
right.
Yeah. And efficiently, it's only not the number of clusters slow down. That's the case. Yeah. Normally, not perfect. Yeah.
Sure.
So back to your very beginning, you have a principal component file.
Yeah.
So do you put all the response and all the features to analyze it together?
Yes. Yeah, and that may be an issue if we're actually fitting them using a PCA to fit a model, but
Yeah,
in this case we weren't doing it.
We were discussing about this. You only use the PCA component for the prediction measure. If you have a discrete variable, a mix with continuous, it can be a problem.
That's a good point.